Find the limit as y goes to 3, y squared minus 5y plus 6 over the square root of y plus 1 minus 2. Does anyone have an answer for us? Oh, I see a hand up.
D.
D as in 4?
Yes.
Great answer. That's it. 4. All right. So, what do you do? Well, first thing is you just plug it in, right? You should always plug in and say what's going on. In this case, we get 0 over 0. 0 over 0 does not mean 0. 0 over 0 means more work. That's right. Now, pro tip, you might need to mix and match tools. So in this case, the tools you need are factoring for upstairs, multiplying by the conjugate to simplify the downstairs. The conjugate is the get rid of square root tool. So we factor the upstairs, we're multiplying top and bottom, because when you multiply, you have to multiply by 1. Well, lo and behold, the downstairs becomes y minus 3, which cancels with our factor. So really our limit can be rewritten as the following expression. So these two expressions are equivalent away from 3. So in other words, not at 3. And now, try 3 again. And out comes 4. So there's our answer. On a side note, you might be saying, what algebra tools are we going to be expected to know? So I want to mention that. So I already mentioned, always check first. Plug in and ask, am I getting 0 over 0? If I'm not, I'm done. Or I made a mistake and I probably missed a sign or something. But if it's not 0 over 0, you're done. Because 0 over 0 is the more work. And you say, okay, well, what does the work entail? Well, you have to do manipulation. We're really all about rewriting. So when we talk about manipulations of limits, we rewrite to simplify. And ultimately, we're really working to cancel. Because we got a 0 over 0, well, that said something made a 0 upstairs, something made a 0 downstairs. Try to get those things to cancel out. So what can you do? Well, you can always add something that's equivalent to 0. You can always multiply by something that's equivalent to 1. And you can cancel terms upstairs and downstairs. And that's more or less it. Now, there's one more thing we will talk about today, but that's coming up. It's not so much an algebra tool. So what algebra tools do you need to be able to do? What are your skill sets? You need to know how to FOIL, expand. You need to know how to factor. You need to know how to multiply by the conjugate. So conjugates are, whenever you see a square root, you're probably thinking like, ooh, I bet you there's a conjugate coming. You need to know how to add fractions. This is your tool set that you need. The good news is, it's not a gigantic tool set. It's relatively small. So if you focus and say, let me get good at these skills, you'll be in good shape. All right. That was our warm-up problem. Some commentary. And our thought for today comes courtesy of Pete Hine. Problems worthy of attack prove their worth by fighting back. And so you're going to see some challenging problems, hard problems. It's okay to have challenging problems. They're worthy to be solved. The harder the problems are, and the more you persist in solving them, the better you get. If you are doing lots and lots of easy problems, and it's like, I'm able to get the answer to all of these problems, you're not learning. You've already learned. You've got to give yourself good, challenging problems. And don't be discouraged. Don't be like, this problem is fighting me. It's like, no, it's good. It's a good problem for you to persist in. It'll help you. It'll help you. And I like some of the things he says. So we'll see more from Pete in the future. All right, so where are we on to? What's today's topic? Well, we're still in limits. And we're going to learn two fairly useful things. So the first useful thing has sort of a nice drawing. And it says, suppose we're in the following scenario. I have a point A. And I have some function g of x. And I got to get another color here that's very distinctive. And I have another function, h of x. And I've drawn them so that they just touch. That's not a coincidence. I really want them to do this. Okay, and the moral here is I have L. All right. So what's our setup? Well, our setup is the following. I suppose that g of x is less than or equal to f of x, which is less than or equal to h of x, for x near a. So, in other words, there's some function in between g and h. And the limit as x goes to a of g of x is some value L. It's the same as the limit as x goes to a of h of x. In other words, g and h are coming together. They approach the same number. So g is below f. H is above f. So f is in the middle. Now the question. If f is in the middle, what happens when we get close to a? What must be true? Just intuition. Go with instinct. What's true?
Close to L.
It's close to L. That's the conclusion. Then, the limit as x goes to a of f of x is L. So I am squeezing this function f between two functions. So this is what's known as the squeeze theorem. Or if you like, the squish. Actually, nobody calls it the squish theorem. But some people do call it the sandwich theorem. So we are squeezing f in between two other functions which have a nice property of that they're coming together. And it's really, the intuition is what you think. F has nowhere to go. I can't like jump out above because h bounds it from above. I can't jump out below because g bounds it below. I have to stay between. So it's forcing me to get close to L. G is close to L, H is close to L, F is in between them, so F also is close to L. All right, so that's the squeeze theorem. Okay, now that seems not so surprising. How can we use it? Well, let's talk about one application. Suppose we want to do the following. What's the limit as x approaches 0 of x sine 1 over x? Now, do you remember what's happening with just the sine 1 over x part by itself? We drew it last time. It's not asymptote. It was doing this, where it was oscillating up and down infinitely often near 0. So the sine 1 over x, that was the case where the limit as x went to 0 did not exist. So just the sine 1 over x, if you just had that, there is no limit. Because it doesn't go to one thing. It's bouncing up and down. But now we've added an x. Okay, so how does adding that x help us? Well, what do we have? We have All right, how to phrase this. Let's talk about our intuition. What's happening to x as x gets close to 0? It gets small. This is good. This is important information. Small. What's happening to sine 1 over x? Well, it's moving up and down. So it's not going to any one particular thing, but can it move up and down by a lot? Can it get arbitrarily high or arbitrarily low? No. How big can it get? It can go up as high as 1 and down as low as -1. I can't jump up here. No, that's not allowed. So it's small. This part is bounded. If I have a small thing, let's just do intuition and we'll justify everything in a second. If I have a small, tiny thing multiplied by something which can't be big, it's a bounded thing. A small thing times a bounded thing should be what? Small. So, what should this limit be? 0. Your intuition is right. So we're going to justify this. So this is in fact right. This is 0. So how do we justify it? Well, we say, aha, we're going to say the bounded part, we're going to bound it. So sine 1 over x is less than or equal to +1 and greater than or equal to -1, because that's always true about sine. So now I'm going to do something mildly like, what? Okay, so let's multiply everything by x. So x sine 1 over x, and -x. Now, I'm just going to put for x positive here for a second, just so we don't get too confused. -x is less than x sine 1 over x is less than or equal to +x. So I'm multiplying. If x is positive, I multiply through. I don't change my inequalities. So on the right-hand side, we say, okay, we have this line x, and we have this line -x. And in terms of our discussion, this line -x downstairs, this is our g of x. And this line positive x upstairs, this is our h of x. So where does x sine 1 over x go between? Well, it goes in between these two. So I'm still going up and down infinitely often, but my up and down is getting smaller and smaller. So this is the curve x sine 1 over x. So it's being squeezed between g of x and h of x. And so the limit will be 0. Now, you might say, well, wait a second, that's for x greater than 0. What happens on the other side? Well, the other side is actually the same idea. But your upper bound isn't x, it's technically absolute value of x. And the lower bound is technically negative absolute value of x. But don't get hung up on details. Focus on intuitions. The intuition says small thing times bounded thing goes small. That's the intuition. Small times bounded goes to 0. All right. And when we ask you to apply squeeze theorem, it will be of that form. A small thing times a bounded thing, that's 0. But there's one other thing you can get from the squeeze theorem. It's a very important thing. And it's actually the reason why we force you to learn radians. You know, calculus is not in degrees. Calculus uses radians. And it's all because of what we're going to learn in the next 10 minutes. I should have paused and said, any questions? All right. Good times lie ahead. We're going to ask the following questions. And I'm just going to say we have an intermediate goal. What's the limit as theta goes to 0 of sine theta over theta? That's what we want, and this is a very important thing. So even without knowing the answer, I've already put a box around it. And yet I feel compelled to double box it, because I feel this is going to be very important. All right, so we have a story to tell. So we're going to get to this in a few minutes. And we're going to say, okay, so how do we get there? Well, let's, for the time being, we'll assume that theta is positive for right now. And we'll handle theta negative in just a second. All right. Well, start with our unit circle. And what we're going to do is we're going to move up along it a distance of theta along the unit circle. So, question number 1. Suppose I take this point and I draw a triangle. What's the area? Well, how do you find the area of a triangle? 1/2 base height. Do we know the base? The base is 1. So, if we knew the height, life would be good. Now, we go back to our trig days. Trigonometry, those were the days. What is the coordinates of this point in terms of theta? Do you remember? The x value is the cosine. The y value is the sine. Now that's when we measure theta in radians. So what's the height? The height is sine theta. So the area, 1/2 base height. Okay? Cool. You're not sure what that is yet. That's okay. Our story's not done. We have another chapter to tell. Suppose I start with this same unit circle. I go up that same distance theta. And now I'm not doing a triangle, but I'm cutting out a wedge. You can think of it as a piece of pie or as some pizza slice, but the whole wedge. Now the question, what's the area? All right, now you might not know this one quite so quickly, but here's sort of a nice philosophy. So imagine that you had, or does anybody know the area really quickly off the top of their head?
Is it pi, or wait, theta over 2 pi r squared?
You're on the right track. Okay. So imagine it was the whole circle. Oh, do you know the...
Whole circle, like the full area?
Well, but just this slice. Do you know how much that slice is?
Just that. Like pi over 2?
The yellow slice. I can tell you the answer, but we can keep guessing.
Would it be pi radius times theta over 360 or 2 pi?
Okay, so let's go through it. All right. So I want the area of my yellow slice. So here's my yellow slice. And it's some area. I'm trying to figure that out. Now I'm going to divide it by the total area of the circle. Now, I claim, It's the same circle, so it's still a unit circle. I know the area of the whole circle. What's the area of a circle of radius 1? Pi r squared, but r is 1. So it's pi. Yes? This is the same as if I just take this part, this angle, versus if I go all the way around. So in other words, it's proportional. The same proportions. Now, this angle has a name. We gave it a name. It's theta. What's all the way around a unit circle? 2 pi. So now, multiply across, what do we get for the area? Multiply by pi, you get 1/2. The pi's cancel, theta. And that's it. 1/2 theta. Cool? That's the hard one. Don't worry, there's another chapter. We'll get one more chance. Okay. Suppose, same circle, unit circle. Same angle, theta. But now, I'm going to go out of the circle, so I want to form a right angle. The question is, how much area do I have there? Well, how do you find the area of a circle? Oh, sorry, area of a triangle. 1/2 base height. Oh, do we have an?
I was going to say the same thing.
1/2 base height. Okay, cool, cool, cool. So base is 1. So area is 1/2 base. How tall is that? Well, do we know this angle here? It's theta. What side do we know? The base, in terms of a right triangle, adjacent side. What side do we want to know? The opposite side. What relates opposite and adjacent? Tangent. The height is tangent theta. Opposite over adjacent. So, now let's take a look at something. Let's compare these two areas. Which one is the bigger area? This one, because it has that little sliver more. So we can say, okay, so 1/2 sine theta is less than or equal to 1/2 theta. Well, you can cancel the halves. And since we're not 0, we can divide by theta. Theta is positive. So that tells us that sine theta over theta is what? It's less than or equal to 1. Okay, so we'll make a note here. Sine theta over theta is less than or equal to 1. Well, now let's look at these two pictures. Which one's bigger? The right one, because you've gained a little bit on the outside. So we have that 1/2 theta is less than or equal to 1/2 tangent theta. But what's another way to say tangent theta? Sine over cosine. The halves, again, can cancel. We can move the theta, and we can move the cosine. So you get cosine theta is less than or equal to sine theta over theta. So sine theta over theta is between cosine theta and 1. Ooh. Nice. All right. Well, let's sketch those curves. One looks like this. Cosine theta looks like this. So, what can we do? Well, sine theta over theta has to go in between. So, if 1 goes to 1, what happens to cosine theta? Goes to 1. So this goes to 1, and this goes to 1. So what has to happen to the thing in the middle? It also goes to 1. Now this one you're like, ooh, cool, Steve, but what about negative values? Well, okay. I'm just going to make a little comment about sine theta over theta. Now just let's plug in negatives. Sine of negative theta over negative theta. Now, what do we know about the sine function?
The negative sign.
Sorry, what?
The negative theta, sine negative theta would be negative sine theta.
Yeah. See, sine is a very unusual function. A strange, weird, odd function. And in odd functions, you can pull the negative out. So this is negative sine theta over negative theta, and two wrongs make a right. Two negatives make a positive. So what it means is that there's symmetry. So whatever happens on the right happens on the left. So you can basically flip it over. So this is true from both sides. So sine theta over theta goes to 1. This is important. Very, very useful. And this only works when theta is measured in radians, which is why for calculus, we use radians. So you got to use your pi's, your pi halves, your pi fourths, and so forth and so on. It all boils down to this fact. This is a good fact. I'm going to give it a star. Yeah, we should know that fact. Okay, now, I like to remember this just to sort of emphasize it to myself. This really says, if I have something, I'll call it blah. If I have sine of blah over blah, and blah is going to 0, what does this go to? 1. As long as what's inside the sign matches with what's below the sign, and the things are going to 0, you go to 1. All right. Now, why is this an important limit? Well, because it bridges trig functions with polynomial. And that's going to be an important bridge as we go forward. Okay. So, a quick example. Find the limit as theta goes to 0 of 1 minus cosine theta over theta squared. We'll do this one together, and then we'll give you one to do in a second here. Now, we see trig, we see non-trig. Whenever we see non-trig and trig, we're like, probably sine theta over theta. So the wheels in our head are turning, sine theta over theta. But before we do anything, what should we check? We should plug stuff in, just to say, do we need to do any more work? So we plug in 0. So this is giving us 1 minus cosine of 0 over 0 squared. Cosine of 0? 1. So this gives us 0 over 0. So what do we know we need? More work. More work. Okay, so we know we have to do work. And because we see trig and non-trig mixed together, we say, we've got to find a way to get sine theta over theta. That's the only way we can bridge our gap. So we say, okay, we think to ourselves, how can we get sine theta over theta? That's what we're thinking. So, what do we do? What do we do? is there anything that makes a 1 minus cosine into a sine? And if there's not, is there anything close to 1 minus cosine that becomes a sine? Sorry, what? I heard somebody say sine squared theta.
Yeah, sine squared theta, that's equal to 1 minus cosine theta? Something.
Almost. Almost. I really like that, your train of thought there. So sine squared theta is not 1 minus cosine theta, but it's almost. Almost. What's missing? A square. Like, wait, yes, this is good. This is good. We have that sine squared theta is 1 minus cosine squared theta. But the problem is that we have 1 minus cosine, not 1 minus cosine squared. Oh. Is there a way to make 1 minus cosine look like 1 minus cosine squared? I see. Multiplied by the conjugate. What? The conjugate can be used for more than square roots? I know. It's like double featured, right? Extra bonus. So, theta goes to 0. 1 minus cosine theta over theta squared. We're going to multiply it by 1 plus cosine theta, but you have to do it to top and bottom, because if you multiply, you have to multiply by 1. Upstairs, we get 1 minus cosine squared, because it's 1 minus cosine times 1 plus cosine, difference of squares. Downstairs, we get our theta squared and 1 plus cosine theta. We don't multiply. You only multiply the conjugate part where it's helpful, not where it's not helpful. I know that doesn't sound very useful, but once you sort of get through the rhythm, it's like, yes, it's helpful because it's simplifying. It's not helpful because it's not simplifying. All right, which becomes the limit as theta goes to 0 of sine squared theta over theta squared 1 plus cosine theta, which we can really think about this as pieces. So we're breaking it up into small bite-sized pieces. We have a sine squared over theta squared. So I can think of it as sine theta over theta, and 1 over 1 plus cosine theta. So I'm just pulling it apart into pieces. The reason I'm doing this is I want to pull it apart into pieces where I understand each part. What happens to the first sine theta over theta? Goes to 1. What happens to the second sine theta over theta? Goes to 1. What happens to the 1 over 1 plus cosine theta? 1 by 2. 1/2. Right? Because cosine of 0 is still 1. Just like it was at the start. So, since each piece converges, then the product is just the product of the individual parts. So what's our final answer? 1/2. And we're done. All right. So now, here's one. Find the limit as t goes to 0. Sine of 3t squared divided by t sine 4t. If I see sine, I think to myself, I have my limit as blah goes to 0, sine blah over blah equals 1. So I say, well, I need to put a 3t squared underneath that sine of 3t squared. By the way, I didn't plug in, but it goes to 0 over 0. So multiply by 3t squared over 3t squared. Same thing, I need to put a 4t underneath that sine of 4t. So I'm going to have a 3t squared, that 1, and I have 4t times t, which gets the 4t squared. Then I have a sine of 3t squared over 3t squared and a sine of 4t over 4t. The t squareds cancel. 3/4 times something which goes to 1 times something which goes to 1, so the answer is 3/4. That's if you have to justify it. All right, now what if you don't have to justify it? The fact that sine of theta over theta goes to 1 says that sine of blah is about blah when blah is 0. That's really what it means. It really says sine of blah is blah. And you should treat it like that. So you say, well, sine of 3t squared, that's about 3t squared. Sine of 4t, that's about 4t. So this whole thing is about 3/4. And 3/4 goes to 3/4. And you're done. And you might say, wait, is that justifiable? Yeah, you're basically doing that. But it's a little bit easier to follow. But again, that's if you're doing multiple choice, you can do that. Long answer, you got to bite the bullet.
Does this, the multiple choice approach, usually only work when it's approaching 0, or?
It works when you have sine of blah is about blah.
So when the sine of whatever is about.
When your blah is not close to 0, forget it.
Okay, so if it was like t approaching 5, for example.
Yep.
Okay.
Yep.
That's what I'm saying. Yeah.
I see more hands. Wow. So how do the 3t squared and the 4t cancel? Well, this 3t squared went to here. This 4t, the numerator of 4t, combined with that t to get 4t squared. The t squareds cancel. You're left with 3/4. The bottom 3t squared combined with the sine 3t squared. This bottom 4t combined with the sine 4t. So that we got the sine blah over blah. So then we could use our rule. So that's what we were doing. See, another question. What is this? This follows because of the limit as theta goes to 0, sine theta over theta is 1. So it's also true that tangent of blah is about blah. But you never really need it. You just need to know sine of blah is blah. Now, I look forward to seeing how the automatic subtitles are generated when we post this online. I don't know how it's going to come across as blah. That takes work. All right. We do have one more idea for today, but the good news is it's very intuitive. And this is one-sided limits. And so what's the goal? So the goal for one-sided limits is saying, hey, limits say, look what's happening from both sides. One-sided limit says, no, don't do that. Look what's happening from one side. So the idea here is we have some point A. So when we talk about the limit as x approaches A from below, and I'm going to use a different color here just to emphasize. We'll put a little minus. So this means from the left or from below. So you only think about what happens on the left-hand side. In a similar way, we can talk about the limit as x approaches A from the right-hand side, and we use a little plus. Notice that we're not putting it in front of the A, we're sort of putting it upstairs, just to keep track of direction. So this minus and plus are just indicating from which direction we come. From the right, or we sometimes say from above. So, just remember the song, right? From the left, from the left. When we want from the left, we put a minus sign up there. Wait, no, it doesn't work very well. But okay, but the point here is just we're looking from one side. Now you might say, why would you do that? Why just look from one side? Well, the simplest thing is you might have something which is a piecewise function. In other words, you have something which is defined in parts. So you might say, oh, well, I'm x plus 4 for x less than 0, and I minus 2x plus 5 for x greater than or equal to 0. So in that case, what do I look like? Well, I look like x plus 4 below 0. Notice there's an open circle. And then I look like minus 2x plus 5 if I'm above 0. So I look like that. So that's one reason. We'll talk about this in a second here. We'll work through it. There's a second reason, which is just might be undefined on one side. So for instance, if I ask, what's the limit as x approaches 2 of the square root of 4 minus x squared? Well, the problem is, what does this function look like? It's the top half of a circle, and it only goes from negative 2 to positive 2. I can't come in from the right-hand side. So this limit, I can't ask the question because it's undefined on the right-hand side. So as written, it would be undefined. But if I say, what happens as I approach 2 from below of the square root of 4 minus x squared? What's the answer? Yeah, just follow the diagram. It's going to 0. All right, so let's do this example here. What's the limit as x approaches 0 from below of f of x? Now, you can use the picture, or you can say, well, it's a piecewise function. So I use the piece just below 0. That piece is x plus 4. So in other words, just below 0 is behaving like x plus 4. And what does that turn out to be? 4. And then I can say, well, hey, let me ask on the other side. So when I have piecewise, I do it in separate pieces because I need to understand how the individual pieces work. So that's the limit as x approaches 0 from above of negative 2x plus 5. And what does that do? It's 5. So, question. What's the limit as x approaches 0 of just f of x? From the left, it said 4. From the right, it said 5. The answer is? Does not exist. So, a limit exists if and only if the individual piecewise things exist. All right. Here's a question. We'll do this one together, and then we'll throw up a fun one. Suppose that f of x is as shown in the figure below. Find the limit as x goes to 0 of 1 plus f of 1 plus x over f of 1 minus x, or explain why the limit does not exist. Now the problem here is that x equals 0, we're at f of 1, which is unpleasant. Weird things are happening here. So we can't just be like, oh, plug it in. Oh, no. So we have to be careful. So we're going to break it up into the two sides. So the limit as x approaches 0 from below and from above. Now here we don't have an explicit formula, so we just have to think about what's going on. So if I'm approaching 0 from below, what kind of number am I? Negative. So what's happening to 1 plus x? What's that doing? It's approaching 1 from which direction? From the negative direction, from below. As I approach 1 from below, what is f doing? F is approaching what value? Negative 2. So the top is going to 1 plus negative 2. Now, again, x is approaching 0 from below. What is 1 minus x approaching? Well, it's approaching 1 minus 0, which is 1. Is it approaching it from below or from above? If I take 1 minus a negative number, am I below 1 or above 1? Above 1. So I'm approaching 1 from above. As I approach 1 from above, what am I approaching? 1. 1 plus negative 2 over 1, also known as negative 1. The limit as x approaches 0 from above. Okay. So, 1 plus x is approaching 1. From what direction? From above. So what value am I approaching? 1. 1 minus x is approaching 1, but from which direction? Below. What am I approaching? Negative 2. 1 plus 1 over negative 2? Negative 1. So, what's the conclusion about the limit as x goes to 0 of 1 plus f of 1 plus x over f of 1 minus x? The answer? Negative 1, because they match. And if they match, then that's the answer. Now, we're basically out of time, but I did want to throw up the multiple choice problem. You can take a quick guess. Given that f of x is the function shown in the picture below, so that's f of x, right? Look at it. It's beautiful. Look at it. Look at it. It's so beautiful. Okay, so what's the limit as x approaches 1 of f of f of f of x? 1, 2, 3, 4 does not exist. The answer is C. There you go. So we'll scan that so you can take a look at it. It's a fun onion problem.